Dear students, the test which we consider in this class is the Kruskal-Wallis test. The Kruskal-Wallis test. Kruskal-Wallis test is a non-parametric alternative to one-way ANOVA. It is a non-parametric alternative to one-way ANOVA. We apply this test when the distribution of populations have same shape. It is not necessary that the populations are normal or any other specific shape. The only requirement is populations from which the variable is taken have same shape, whether it is normal or not. Normality or any specific shape is not required. Unlike Mann Whitney test used to compare two means if the distributions are identical in shape, Kruskal-Wallis test is also based on ranks. And if two or more observations are tied, we will give the mean of the ranks to each observation. Now, as an example, suppose that independent samples are taken of cars, trucks, and buses. Cars, trucks, buses. And suppose also that number of miles driven by cars, trucks and buses last year is noticed in thousands of kilometers. And suppose that many cars are taken, many trucks are taken, many buses are taken. And suppose also that the miles driven by these three modes of transportation are noted. And we want to test whether a difference exists in the mean number of miles driven by them. So our null hypothesis is mu1 is equal to mu2 is equal to mu3. We want to test the hypothesis mu1 is equal to mu2 is equal to mu3 against h1. Not all these means are equal. Not all these means are equal. And remember this, to apply this test, normality is not required. What is required is these populations have roughly the same shape. Then, as we apply Kruskal-Wallis test on ranks, we rank the observations on cars, trucks and buses. Rank this combining all the observations. And the ranks are 9.8 and take the mean values 9.85, then 9, 19.67. These are the ranks obtained. Suppose 9.85, 9 and 19.67 are the mean ranks after ranking the miles. And if the number of miles driven is roughly equal, these mean ranks must be roughly same. Or what we test here is not the actual miles and the means based on this, but what we do is we rank the miles and the mean ranks are compared. And if the mean ranks are similar, then the number of miles driven by cars, trucks and buses will be more or less same. If they are different, then the mean ranks or the average number of miles driven by these three modes of transportation are different. And to measure the variation among mean ranks, we use the concept of treatment sum of squares that we have considered earlier, studied earlier in the context of one-way ANOVA. Now we use treatment sum of squares of ranks. Treatment sum of squares of rank. And to decide whether that quantity is too large, we also compute or we compare it with the variance of all ranks expressed as SST, total sum of squares, divided by n minus 1. And as we have discussed earlier, if SSTR is much larger than SST, it is evidence against H0. The same principle which we have discussed in the context of one-way ANOVA is used here. So SST is total sum of squares of ranks, n is total number of observations. Now the calculating formulas are same as we have discussed earlier. The only difference is SSTR, treatment sum of squares, SST, total sum of squares, are calculated on ranks, not on original observations. Now, the test statistics for Coxel values test denoted as H is equal to SSTR by SST by n minus 1. H SSTR by SST minus n by 1. And if the value of H is very large, then it means that the variation among mean ranks is large relative to variance of all ranks. That is, variation among ranks, SSTR, is much larger than variance among ranks. And so H0 is rejected. In this example, SSTR is, the value of SSTR is 537.475. The value of SST is 1299. N is 25. So H is equal to, applying the formula, 9.930. That is the value of H obtained for this example. Now the question is this H large enough to conclude that H0 is rejected? Large enough to conclude that H0 is not true. To answer this question, we must first examine the sampling distribution of the variable H. We must first examine the sampling distribution of the variable H. Now suppose that k distributions, one from each population, has same shape. K distributions, one from each population has same shape. Then for independent samples from k populations, the variable h is equal to SSTR by SST by n minus 1 has chi-square distribution with n minus 1 degrees of freedom. So this quantity has chi-square distribution with not n minus 1, k minus 1 degrees of freedom. K is the number of populations. And so we can use the chi-square distribution to test the hypothesis that mu1 is equal to mu2 is equal to mu3 or mu k as it is. Now, for computing h by hand without using a software, the computing formula is h is equal to 12 by n into n plus 1 into sigma j is equal to 1 to k r square j by n j minus 3 into n plus 1. This is the computing formula. And this formula is only for a reference because we have softwares for all these calculations. You are supposed to know only the theory behind Cruxell-Wallis test. And what is Rj? Rj is the sum of ranks for the jth population. So R1 is the sum of rank for the first population, R2 second, etc. Nj is the sample size. And remember this, the null hypothesis is rejected only when the value of h is very large. So, Cruxell-Wallis test is always right-tailed. Right-tailed. Not only that, in this demonstration, we have suggested that the test is used to compare different means. We can use this test to compare different median also. And in some softwares, you will get median difference as the testing procedure. It depends on which software you use. In the Minitab software, for example, median differences are given. So it depends on the software. Now, this is the Cruxell-Wallis test. Now, let me conclude. Based on 4 assumptions: simple random samples, independent samples, same shape populations, and all samples 5 or greater. All sample 5 or greater. And this assumption is required only when chi-square is used for the approximation of h. If this assumption is not satisfied, all samples not 5 or greater, you have to consider the critical value from h table. Now the steps. The first step is h0, mu1 is equal to mu2 is equal to etc. mu k. h1, not all these means are equal. Second step is decide alpha, the level of significance level. Then rank data from all samples combined, starting with the smallest. Compute the value of the test statistics. Then find the critical chi-square value, chi-square alpha, with the n minus 1 degrees of freedom. Then take a decision. And in our example, if we assume that alpha is 5%, the value of h is as 9.930, and chi-square value for 3 minus 1, k is 4, so 3 minus degree 1 is 5.999. So naturally we reject H0 because the value of H obtained from the sample is larger than the critical H. So H0 is rejected, mean values are not same. And this is the non-parametric alternative to Cruxall-Wallis test. Cruxall-Wallis test.